Okay. Good morning, everyone. Thanks for the introduction. I'm Zhengqi Chen from Crucianelli University of London. I'm a PhD student right now. This work is supervised by Lorenzo Jamone, who's a roboticist, and Elisabetta and Laura, who has a background in psychology. So this work explores how humans and robots can use only touch to detect hidden objects in materials like sand. Now let's get started. In everyday life, we rely on both vision and touch to interact with the world. For instance, spotting a cube on the table is easy with our eyes. But if we had to find it using only the sense of touch, it would take more effort, involving exploration until our finger make contact. The challenge intensifies when an object is completely buried in granular material, such as sand. Could we detect it actually before touching it? Certain animals like shorebirds do this remarkably well. They probe sediments with their beaks and sense prey through subtle force changes. Humans are thought to have similar abilities, using the sensitivity of our fingertips without relying on the sight. However, no prior study have delved into the specifics of these human skills. This leads to our research question. Can humans and robots detect buried objects in granular material like sand using only touch? And if so, how effective is this tactile perception? A key concept here is called the white zone model, which explains how touch works in granular material. When a finger or any factor moves through the sand, it only disturbs the particles within the wide-shaped region ahead of it, leaving the rest untouched. This zone size can be calculated based on the finger's dimensions and the sand particles' properties. In our scenario, the finger initially senses only the force from the granular material when it is far from the object. But as the finger approaches the buried object, the disturbed particles eventually interact with it, creating an additional force that's felt at the fingertip. This actual force signals the object's presence before direct contact. So our study is the first to demonstrate human tactile detection in granular material through controlled experiments where a parallel robotic study provides a comparison. Together, this validates the white zone model and show how it applies to both biological and artificial systems. For our human experiments, we used the sandbox with 4 fixed locations where a cube could be buried, or not all, to keep participants unaware of its presence or location. We first measured the finger size of each participant. After a few familiarization trials, they inserted their finger straight into the sand and moved it forward at a steady speed, guided by an LED strip mounted on the box to maintain consistent pressure. They were required to keep a vertical insertion gesture along the raking and to stop as early as possible before they touch the object once they sensed it. Then we recorded the stopping points relative to the actual cube location. So for each of our 12 participants, we collected data of 18 raking trials. Then for our robotic experiments, we replaced the human finger with a custom tactile sensor of similar size, mounted on the robotic arm. The sensor consists of 4 tactiles that detecting forces in 3 directions. And we maintain the same experiment setup, such as the raking depth and the speed, the type of the sand particles, the same as the human experiment. What's different here is that the cube stayed in a fixed location, but we varied the starting points to create different trajectories. In each trajectory, the sensor advanced until it was 2 centimeters from the cube, collecting force data along the way. In total, tactile readings from 120 trials of raking were recorded for the following training, validation, and testing. Both humans and robots interacted with the same sand type, so we expected a detection range of about 7 centimeters, according to the white zone model. To test this in the robotic data, we labeled the sensor readings using 5 distance thresholds from 3 centimeters to 11 centimeters. Data points within the threshold from the object were labeled 1 as detectable, and those farther away were labeled 0 as undetectable. For each threshold, we trained a long short-term memory model to predict detection. Therefore, the 5 thresholds result in 5 distinct LSTM models for object detection. Now let's examine the human performance. For object present trails, the wide zone model predicts an average detection range of 6.9 centimeter, as shown in the yellow part in this plot. Then to account for the noise, stops within 2 centimeters of the cube. The blue area in this plot were considered as direct touches instead of detections. And this is also the reason we decided to end all our robotic trajectories 2 centimeters from the barrier cube. And as you can see, when the cube was in location 1, most stops occurred within the predicted range, like this yellow area. And this pattern is consistent across all the locations. Now let's look at the trails with no barrier object. The participants correctly identified the absence in 58 out of 72 trials, with the remaining 14 trials showing a random-like distribution. Then for the robotic results in the object-present trials, this plot displays the first reported stops from our 5 models. As the model threshold increases, the prediction results are shown in color from dark to light. The model with the lowest threshold of 3 centimeters is displayed in the darkest blue. The yellow band marks the wide zone's predicted range, 7.1 centimeter. Models with threshold below this range reported most stops within it, with medians near their thresholds, showing that smaller thresholds enable more accurate and timely detections. Models with larger threshold lack this clear pattern, showing a broader distribution with peaks beyond this predicted range. Then for the object-absent trails, the x-axis of this plot represents the distance from the starting locations to the first reported stops. The 3 centimeter model successfully identified most of the trials, with just 2 false positives reported at the end of the trajectory out of 20. But except for that, higher thresholds models stopped early across 20 trials, all the 20 trials, as larger thresholds led to more premature detections. Comparing human and robotic performances, we focused on the robotic model with a 7 centimeter threshold, the largest threshold validated according to the wide zone theory. And the object present condition, as shown in this figure, the robot demonstrated a slightly larger detection range with an upper interquartile range value of 6.59 centimeter, compared to 4.05 centimeter for human participants. This indicates that after eliminating the outliers, the robot's detection occurred closer than 6.59 centimeter from the object. However, in object-absent conditions, humans outperform with higher precisions, avoiding false positive better than the robot. In conclusion, our human study provides for the first time that people can detect barrier objects in sand using only touch, with thresholds aligning to the wide zone model. We also show that robots trained on similarly labeled data achieve comparable detection, validating the model across both. Overall, this bridges human intuition and robotic precision, opening doors for applications like search and rescue and planetary explorations. Thanks for listening. I'm happy to take questions.
So thank you. Do you have questions? Two. So just meanwhile, can the next presenter come so we can set up?
Hi, thank you for the great talk. It was super interesting, and I was wondering, how do you envision these extending beyond the, let's say, one-dimensional line towards the object? So do you envision these could be potentially useful for like two-dimensional objects in a plane of sand and exploration towards that? Like, do you have any insight into possible expansion of this?
Thanks for the question. So our work is mainly to provide a baseline, a human experiment baseline, to see what is the tactile perception capability of human. And for an extension of this work, it's possibly to use a robotic way, like to do similar tasks. But the focus of our task is not in a very large area. Instead, it's relatively a small area, and the target will be relatively small. And it's mostly focused on the shallow layer of the granular material. Yeah.
Thank you.
Yeah, thank you for the nice presentation, very clear. I was wondering how scalable this is with respect to the distances over which you can register anything, and how that depends on the properties of the granular material, because it's only like centimeter scale.
Yes, yes. Thanks for the question. Yeah. So I didn't put too much detail here. So the wide zone model, it requires the parameters from like two main targets. So the size of the anti-factor, in our case, is the human finger, the length of the human finger, and the parameters for the sand particles. In our case, it will include some parameters like friction, friction angle, dilation angle. Those kind of parameters is actually need experiment to get the exact value for the exact particles. But in our case, we actually didn't do such experiments. We based on the experiments, we choose a value in a certain range that we think makes sense, and our results validate our assumption.
Is there other question? I don't know if you.
Hi, thank you for the talk. I was just curious how you might think of extending this to environments where you maybe don't know the properties of the sand. So I guess with the bird can probably do this no matter how much water is in the sand. That probably changes the properties. So do you have any thoughts about how you might operate in environments with unknown properties of sand?
Your question will be about how we determine like the exact granular material we're using, right? Yeah. So for the granular material, there's a lot of type of granular material. For example, like the sand, the snow, the boulders, they all have different properties. But for the sand, the exact sand we're using, so based on its size, so based on its weight, based on its volume, we can have a rough assumption about, like, for example, the density and the relative Young's modulus, those kinds of parameters, and we use that for this model. Thank you.
So thank you very much. Let's applaud our speaker.